by European academies. I'll just say a few words about Academia Europaea for those of you who may not know too much about this organization. So it's one of the European networks involved in the scientific advice mechanism of the European Commission. And it is one of the partners, the only one of the partners who is a straightforward kind of classical academy that elects members purely on the basis of scientific excellence. So it is the Academy of Europe. And in that sense, I think it is quite important academy as European science draws together and becomes an important force in this world. Maybe this is even more important now than it has ever been before. I think we are at the very start of the decline of US science because of the extraordinary policies that happened there, and European unity also in the scientific world is therefore of particular importance. We have more than 5,000 members, as said, all elected because of their scientific excellence, including a very large number of Nobel laureates. Uniquely, this academy operates through a network of hubs across Europe. And you can see on this map here the various knowledge hubs from Bergen in the north, to Barcelona in the south, to Tbilisi in the east, and Cardiff in the west. So the Cardiff hub is the principal coordinator of the Academy's work for SAPEA and therefore for the scientific advice mechanism. And Louise Edwards, who is here happily, is the manager of the Cardiff Knowledge Hub, and she has played a very big role in coordinating particularly the report on the solar radiation modification. And Louise will give a little bit more detail about how SAPEA operates. SAPEA stands for Science Advice for Policy by European Academies and is the organization that provides the scientific evidence for the European Commission's scientific advice mechanism. So without any further ado, I wish you all a very interesting and exciting webinar. The other two that we have had were very successful. And I hand over now to Louise to give a short orientation about SAPEA. Over to you, Louise.
Thank you, Ole. Yes, my name is Louise Edwards. This is the third and final in a webinar series on SRM. There are two more that look at social science aspects and also a broad sweep of strategy. And the recordings of those and the slides are available on the website, so look out for those. Afternoon, speakers. And in speaker order, we're starting with Simone Tilnes, and then Gabriel Chiodo, followed by Johannes Quas. And they're all members of the SAPEA Expert Working Group on SRM. The fourth speaker will be Naki Nakasenovic, who's Deputy Chair of the Group of Chief Scientific Advisors. And then we'll take some comments from Dusan Hrenek, who is the Principal Advisor of the Directorate General for Climate Action at the European Commission. Welcome to you all. The format of the webinar is that I'll provide a very quick little bit of background. We'll then have opening presentations from the first four speakers, some brief comments from Dusan, and then there's an opportunity for audience interaction. So please use the Q&A box if you'd like to ask some questions to the panel. Just to tell you a little bit about what the scientific advice mechanism is, it's called SAM for short. And the SAM provides independent scientific evidence and policy recommendations to the College of European Commissioners on any policy relevant subject. including on issues that the European Parliament and the Council consider to be of importance. There are three parts to the SAM: the group of chief scientific advisors, the SAPEA consortium, and they're supported by the SAM Secretariat at the Commission. The advisors are a group of 7 highly qualified experts from different disciplines, different backgrounds, and it is they who make the policy recommendations to the European Commission. SAPEA is an acronym standing for Science Advice by European Academies. It brings together experts from 120 academies from 40 countries across Europe. And it's SAPEA that provides the independent evidence reviews that inform the recommendations of the advisors. So very quickly, this shows you how it works. We have a request from the European commissioners. We review the evidence. The SAPEA working group produces an evidence review. The advisors make policy recommendations, and both of those reports are then handed to the European Commission. So on SRM, back in 23, the then Vice President Timmermans asked the advisors to assess the risks and opportunities associated with research on SRM and its potential deployment. And there were 2 scoping questions. The first one looked at risks and opportunities associated with research on SRM and its potential deployment. And the second question asked about options for a governance system on research and potential deployment. So my last slide shows you how the SAPEA group worked. This was a working group of 20 experts from different disciplines, different countries, different career stages, different stances on SRM. And their report, which you can see on the right-hand side, has an introduction, 3 chapters on the science and technology background and issues, which is what we're going to focus on today, 3 chapters on the social science related background and issues, and some policy options. So enough from me, and I'm going to hand over to Dr. Simone Tilmes, who's going to start us off with the presentations. Over to you, Simone.
Thank you, Louise. So I will talk about the solar radiation modification technologies, and I was honored to be on the panel. Thank you for having me as a member. So as a motivation, we do see more interest into the topic of solar radiation modification, in particular in recent years, since we see continued warming, we see growing impacts to societies and ecosystems with global warming already at this stage. And we know that temperature will continue to increase until we reach net zero emissions. As you can see on the left, we are at a lack of ambition to meet required temperature targets and also the emission targets, and current policy actions fall short to reach those. We may reach up to 3 degrees of warming, so a doubling of what we have seen already by now, by the end of this century. So the question is really, should we consider these technologies as potential climate responses in addition to mitigation to help reduce some of these impacts, to maybe prevent reaching climate tipping points and other impacts? And so what we really need to do is look at questions on what are the benefits, side effects, and risks to make well-informed decisions when it's time and to know what the impacts would be. Next slide. So I want to go over some of the proposed technologies here. And as we know, greenhouse gases in the atmosphere warm the planet, they warm the atmosphere and also the surface. And to counter this, the idea of solar radiation modification would be to make the planet a little bit more reflective, basically reflect some of the incoming sunlight back into space to cool the surface. And technologies that can be applied here and mostly discussed, as shown in this figure on the right, One of the most prominent one is stratospheric aerosol injection. This is similar to what volcanoes do, injecting, the idea is to inject particles in the atmosphere above 20 kilometers. Those will distribute around the globe and therefore reflect some of the sunlight and cool the surface. Other methods will look more at clouds. Marine cloud brightening can make clouds a little brighter in injecting sea salt, or we can also try to remove those clouds, the cirrus clouds that actually warm the planet. Other methods look at surface brightening, making roofs wider or surfaces wider to reflect sunlight. And also discussions and research is starting on space mirrors, which are very expensive at this point, but maybe something viable to be in the future, to put mirrors between the sun and the earth to reflect some sunlight. None of these technologies are perfect to counter greenhouse gases, and therefore we really have to look at the details. But in the next slide, please the next slide, I want to talk a little bit about what potential these technologies may have. So a global approach like stratospheric aerosol injections may be able to slow the rate of warming to maintain global temperatures, or to even reduce global temperatures, and therefore reduce potentially the risks of the global warming. If they are applied in addition to strong mitigation and carbon dioxide removal, they may help us by some time, so we have more time to quickly reach net zero and potentially reaching tipping points, as I said before. And more local approaches, including like marine cloud brightening or surface brightening, could help to prevent these ecosystems that are already impacted by climate change a bit. And so just pointing out again, current research is based on indoor research, modeling, and lab studies. Outdoor experiments have not been performed at any relevant scale. Next slide. So, and you can do a few more so we see all the, yes, that's it. Thank you. So volcanoes are certainly one of the analogs of stratospheric aerosol injection. What we can see is that after large volcanic eruption in the past, we can measure temperature reductions throughout the globe. You see the slight reduction in the red curve on the slide on the left after large volcanic eruptions. And for example, for Mount Pinatubo, which injected a large amount of sulfur into the stratosphere, we see a cooling of about 0.3 degrees of Celsius, even though there's a bit of an uncertainty how much aerosol were actually injected. But these volcanoes can be used to research the effects of this methodology. However, it's not a perfect analog because it's just one injection at a specific time. And so really researching stratospheric aerosol injection as a method, we do need other things like computer models to understand the impacts and risks. Can we go to the next slide? Yes, so Earth system models are use really physical processes and equations to describe the atmosphere, land, ocean, and cryosphere. And these are very sophisticated models that are used to research the future climate, but can also be used for solar radiation modification. And as you see here on the middle panel, the atmosphere, especially the stratosphere, is quite complicated. We see the movement of air masses. If you advanced one more, Luis, we see, there are potential injection locations of these aerosols. These aerosols have to be moved in the stratosphere. They change chemically. They will be removed again after some time. So these models often, many Earth system models often don't have all the complicated processes, and only some models can describe this. But all of these show that we can actually achieve a certain amount of cooling depending on the amount of injection. And so there's still a large uncertainty how much that cooling would be and what the regional impacts would be. But we are confident that the cooling can be achieved. Next. So we can use these Earth system models to look at potential scenarios of applications. Some are more desired than others. On the left, you see an example of a very strong SAI scenario, considering we would fail to put mitigation sufficiently into place and temperature continue to increase, solar aerosol injection, stratospheric aerosol injection could be applied increasingly with strength to counter this warming. But with the increase of injection annually, we also see increasing side effects and risks. One of those is, for example, the termination effect, that if this application would be suddenly terminated, temperatures would rush back to the warmer conditions, which could be devastating for ecosystems and societies likely. However, the more promising scenario that is discussed is the peak shaving scenario that would be used more as a stopgap measure in addition to mitigation and CO2 removal to really sustain our temperature over a certain time period while we would still not reach these targets that are needed without those applications. Those methods show much fewer side effects and risks. And this really shows, the research has shown that applications of SRM would be much more reasonable in addition to mitigation and not as a substitute. And the next slide. Other ways to look at solar radiation modification in models is we can explore the best way how this could be applied to show the most benefits and the least side effects and risks. And that really depends on how we inject. For example, we can do a lot of model studies. So for example, what you see on the right are 4 panels of temperature that compare the temperature to present day conditions. When we do no stratospheric aerosol injection, we see that strong warming we were talking about at the current policy measures about. If we apply SRM in the other 3 panels, we see that temperature much closer to present day, but it really depends on the details how we inject, how well we are doing with that. Like the top right slide, injections at the equator at a single latitude will show some uneven cooling, while other methods can be more beneficial. And this is something that can be worked out. Next slide, please. And so the models, and this is my final slides for the larger picture, is strategy also matter. And in recent years, we're looking more at what materials could be injected. In volcanoes inject sulfur, but we could as well also inject other materials, aluminum, calcite, or even diamond, as not shown here. But those impacts, those materials impact the atmosphere differently. On the left, you see that all of those methods cool the troposphere equally about, but the stratosphere may show other changes like warming, and that can have impacts on the winds in the atmosphere, as shown in the lower left panel, depending on what material is used, and that also can have different climate impacts. And I do not go into more detail now. It also can change stratospheric ozone effects and other risks. But with this, I will hand it over to Gabrielle to talk about the impacts and risks. Thank you.
So it was also my honor to be part of this team. I welcome everyone to my talk, which will be focusing on the stratospheric aerosol injections, which has been nicely introduced by Simone, and I will leverage on what Simone already said in terms of projections and future scenarios. So next slide, please. So SAI, stratospheric aerosol injections, aren't a climate fix for all regions. While models show that SAI can consistently reduce global mean surface temperatures by mimicking volcanic eruptions, the effects on temperature and precipitation are very uneven regionally. The geoengineered climate would, in other words, be different from a climate with mitigation via abated greenhouse gas emissions. For example, on the left, you can see that SAI would not be able to cool Eurasia very well, and particularly also the Arctic. And a robust feature in model simulations is also the widespread drying. Globally, we would dry the climate even with respect to climate change without SAI. And on the right, you can see the impacts on precipitation regionally. And you can see that the tropics would be disproportionately affected by the decrease in precipitation. So please turn to the next slide. So this is one of the side effects, but there are also other side effects that are rather positive. namely the changes in the extreme events in the future. We know based on modeling alone that SAI may be able to mitigate some climate extremes. Namely, it could reduce tropical cyclone intensity and wildfire risks compared to mid-level scenarios of greenhouse gas emissions. For instance, on the left, you can see a study showing that SAI would reduce tropical cyclone activity and hurricane frequency by up to 20 to 30% with respect to a greenhouse gas emission scenario of mid-level RCP 4.5. And also an SAI scenario would project a 15 to 30% decline in the burned areas in fire-prone regions like the Amazon and Australia. And on the right, you can see actually that quantitatively with respect to several emission scenarios like the SSP 245 and also the high emission scenario SSP 585. But here is a critical gap, and maybe we can get to the next slide, please. SAI does nothing, the SRM in general does nothing to actually counter ocean acidification. In other words, we don't solve the root cause of climate change, namely the increased abundance in atmospheric CO2. Even with cooling, rising CO2 levels would continue to acidify oceans, threatening marine ecosystems. By 2100, models project a 150% increase in surface ocean acidity under high emission scenarios with SAI, worse than moderate emission pathways. And here you can see that quantitatively at the top in terms of ocean and acidification, and at the bottom with SAI. So we cool the climate, but we still have acidification as one impact of CO2. And shell-forming organisms like corals and plankton would suffer, remain at risk based on some work on calcification collapse. Next slide, please. Another risk introduced by SAI is Antarctic ozone depletion, as shown in the last quadrennial ozone assessment led by Simone. SAI forcing of strong magnitudes would suddenly implemented to avoid overshooting, for instance, of 1.5 degrees Kelvin to comply with the Paris Agreement would undo the progress achieved with the Montreal Protocol, delaying ozone recovery by decades. As shown in the time series in the center and on the right-hand side, you can see the lines with peak shaving and strong SAI showing what SAI would do to Antarctic ozone with respect to not doing SAI, which would be the black line. You can see that we essentially delay the ozone recovery by about 2 decades. And in one case, we would catch up, namely in the peak shaving scenario, and in another case in which we continue doing SAI, we would never catch up with the projected recovery. And we have, next slide, please. Another risk we addressed in the report are the health impacts from SAI. And in this respect, I should say there aren't that many studies, but we assessed those that are there, and they show a double-edged sword. SAI would reduce heat-related mortality, but increase deaths from PM 2.5 exposure due to the sulfate aerosols settling from the stratosphere all the way to the Earth's surface. Meanwhile, lower surface ozone could also save lives in polluted areas, and that would also be an effect of SAI. So this paper by Eastham estimate that these competing effects could result in a net mortality change of about 10,000 deaths per year, which is nonetheless 1 order of decade less than climate change, for instance, when it comes to heat waves and also pollution. So next slide, please. Another environmental side effects of SAI would be that it would literally change how we see the sky. So we can see in a study shown on the left-hand side how sky clarity degrades with higher aerosol optical depth, which is a reminder of what a planetary scale intervention would look like. The widening effects from aerosols might reduce direct sunlight by about 20 to 30%, also altering photosynthesis. Some plants really like diffuse light, and we would have more diffuse light. Other plants may actually suffer, as, for instance, tropical plants might actually rely more on the direct sunbeam. So the net result on the plants highly depends on the region and vegetation type. Please, next slide. Another element of interest for society are crop yields. The interplay between temperature, light, and water availability makes it extremely difficult to precisely predict the effects of SII. But we know that cooling would benefit wheat in temperate zones, for instance, but it would also reduce maize productivity in the tropics due to rainfall shifts. So there would be really a strong regional variations depending on the crop type and climate feedbacks that would happen in the future. Next slide, please. And this is actually my last slide, showing a list of takeaways. So here are the limitations and unknowns from SII. So the key point number one is that SII remains a high risk and low readiness strategy. Models that our research is based upon in terms of risks lack the resolution of critical processes like aerosols, microphysics, and clouds, and ecosystem responses. And also technologically, we lack the aircrafts capable of doing the stratospheric delivery that we would need. Most critically, SII addresses the symptoms and not the root cause of climate change. But it's important to highlight that side effects are also highly dependent on how much warming we actually want to offset and how we do the injections, as Simone Tilmes said. So taken together, SII is a sort of a paradox. It's a tool to slow warming, but also we may have more inequalities and some other side effects in the ecosystems. So we need to really understand more in detail how these side effects work with better models, more observations, to actually really consider these as a temporary measure to fight climate change. Thank you.
Yeah, thank you very much. And Alan, nice to see you. You're of course right that cloud brightening is another method that merits discussion. So that's we should have maybe given an overview of what the topics are that we discuss. So the ones which I want to present are cloud brightening, limited area, and also some of the prerequisites. Could you advance, Louise? Yeah. So the idea behind this cloud brightening is sort of a bit what we see here from these ship tracks. That's over ocean ships emitting particles. And these particles, aerosols, they serve as cloud condensation nuclei, and each cloud droplet forms on such a nucleus. And so if there is more aerosols, there are more droplets, and more means there is more surface on which the sunlight can be scattered back to space, and that makes the clouds brighter. That's an effect which we see, for example, after shipwrecks, but we have documented this plenty of times. So the idea behind this cloud brightening is to seed clouds. And seed clouds here, of course, with the idea that these clouds are then brighter and reflect more sunlight back to space. I wanted to make the link to cloud seeding in terms of weather modification. Weather modification has the intention to either stop rain or hail or produce it. And this analog is quite interesting because there has been a lot of research into it, and we still, and it's still a very uncertain. The concepts are clear, but the results are completely unclear. Now, there's good reason to think that maybe for cloud brightening, the results are less difficult to obtain than for precipitation, because that's also constrained by other physical principles like mass conservation, but still it highlights the uncertainties. Next, please. And just to say some of these uncertainties, this is from a paper a large group of scientists puts together on the challenges in particular for modeling, because as we saw also in Simone's and Gabriel's presentations, that's how we study solar radiation modification, their caveats, etc. By the way, one thing which I wanted to say actually upfront and forgot is this is a pure research thing. We are interested in understanding what's going on, and you will see, I mean, we didn't see anybody in the entire group that put together this evidence review report. Not a single person intends to actually advocate for doing this. It's understanding understanding the problem. but nobody really would no expert would advocate doing this anytime soon. Except of course for the points that Simone highlighted very early on in the future. Yeah, with maybe tipping points, catastrophic climate change. That's a thing when maybe future generations need to be equipped with this knowledge. Still, I wanted to say very clearly, we're not advocating this, we are researching it. And here are a couple of examples on the problems which we still have in models, in particular for this cloud brightening, because we need to understand intricate turbulence processes and intricate, very scale interacting processes. Clouds are 10 micrometers large and their interaction matters. And that has consequences up to the global scale, and these are the complications. Beyond that, of course, how to exactly spray the clouds is an open question. Next, please. I wanted to say a thing on this idea that what Simone said, this temporally limited SRM, I think nobody would ever even think about this unlimited SRM global scale. But beyond temporarily limiting it until measures for negative carbon emissions, for example, become effective, or surely reduction to zero of the anthropogenic carbon emissions. One could, in principle, also discuss limiting SRM in space. And that's from a study, a very, very simplistic view on climate change economically. But at least it gives a hint that's how the gross domestic product, spatially resolved, is correlated to temperature. And we see it's positively correlated to temperature in the high latitudes. Economy, without any second order, more complicated effects, would basically benefit from warmer temperatures in many high latitudes, and it would suffer a lot in low latitudes. So the preferences are very different depending on region, which of course makes governance very, very complicated. But one should, of course, also say limiting anything in the atmosphere in space is really impossible. Every pollution has an effect transboundary. So it's only to a certain degree this is conceivable. Next, please. And whatever we do, we have seen this in the chat. I have monitored before I was speaking a bit. We have seen the problem that we only know things from models. These models are imperfect. So in order to really implement things, we would need to trust that we can anticipate the effects and side effects, ideally all of them. For example, here is an example of a simulation where we implemented regional solar radiation modification, and we see, yes, on what we call effective radiative forcing, that's the energy budget, that works approximately, but then down below the surface temperature change, we see these effects in many places. And in order to a prerequisite to SRM deployment, even regionally, would be trust in models. And finally, the last one is we also would need, not just for modeling, but we would also need to monitor. We would need to detect whether even a large-scale field experiment takes place. And certainly the deployment, whatever limited or large-scale, whatever method, cloud brightening or stratospheric aerosol or whatever, we would need to observe it. And typically we would expect this has to be done from satellite. Yeah, this is an example where people detected the pollution from cities, how they change clouds. But in a similar sense, we would need to be able to detect it and quantify the effects, and ideally also quantify the side effects. And that was my last slide, and I hand over, I think, to Naki.
Yeah, thank you very much, Johannes. It is my pleasure to present the 5 policy recommendations of the group of chief scientific advisors on SRM. They are based on the evidence review that you just heard from the colleagues and in response to the 2 scoping questions. But let me first recognize my colleague Eric Lamban, who together with me was a co-lead on this on this scientific opinion on behalf of the chief scientific advisors. Next slide, please. Luis has already presented the two scoping questions. Let me just say very briefly. Number one is that our task was to address risk and opportunities associated with research, but also potential deployment of SRM. And the second one, already in the chat I've seen discussed, is what are the options for governance system, both for the research and potential deployment. Next slide, please. And I will go through all of the 5 policy recommendations. Our first one is central and perhaps most important, namely to put high priority on reducing greenhouse gas emissions as the main solution to avoid dangerous climate change. And that's consistent with the EU policy of net zero by 2050 and 90% reductions by 2040. So continuing emissions reductions and vigorously increasing them, and also adaptation to climate change, is very important to deal with the overshoot that you have seen in Simone's presentation. And we basically know what the solutions are: efficiency improvement, the replacement of fossil fuels by carbon-free sources, sustainable land use, enhancing the sinks, hopefully through nature-based solutions, but also sustainable biomass in conjunction with carbon capture and storage could produce net negative emissions. Then CCS together with fossil fuels, and if that's all not enough, then direct carbon removal from the atmosphere. But most important of our recommendations is to invest in research and deployment of climate mitigation and adaptation. Next slide, please. This is very similar again to what Simone has shown in the left corner. It's not projected correctly, but I will just explain it. In the left corner, you have the historical increase of the global mean temperature. And as you can see, unfortunately, last year was 1.5 degrees above the pre-industrial level. So we are in the lower range of the Paris Agreement. And January to January was actually 1.75. So we are in the middle of the Paris Agreement and pre-programmed to overshoot the Paris Agreement. So again, emphasis on mitigation and adaptation, negative emissions. This will be the major ways of coming down, but perhaps SRM could overshoot some of the, shave some of the overshoot on the temperature change. Next slide. But as you have heard, there are many risks and uncertainties associated with SRM. And this is why our second recommendation is to agree on the EU-wide moratorium of SRM deployment that could be probably reviewed periodically as the science progresses. But there is insufficient scientific evidence that SRM would avoid dangerous climate change. You have heard acidification would continue, there would be rainfall changes and so on. But importantly, our second part of our recommendation here is that because of these uncertainties, deployment of SRM would be inconsistent with the precautionary and do no harm principles that are central to the European Union. Next slide, please. Our third recommendation focuses on the global governance system and possible role of the EU in the negotiations about non-deployment of SRM. And basically, our recommendation is that this should be consistent with the relevant international, but importantly, EU law as well. It should involve public consultation, both at the national level and internationally, that outdoor experiments and research should be limited, very limited, and under strict ethical and other rules. Perhaps importantly, and I've seen that also mentioned in the chat, there is a risk of militarization, a so-called dual purpose of SRM. Just think about the deployment aircraft. But this is why we recommend that observation system should be enhanced of Europe, so that in order to be able to detect any rogue or any other deployment of SRM if it occurs, and that Europe should oppose the cooling credits that might emerge from SRM. Next slide, please. Now, since this is about technology, I just wanted to say a few words about our box 3 that deals with the delivery technologies of the of sulfur injection into the stratosphere. And you know the cost estimates are exceedingly wide of this possible of deployment by the aircraft, anywhere between 18 and 117 billion dollars per year to offset maybe half a degree to a degree of warming. And as you have heard from the colleagues, there are other delivery mechanisms, but we are focusing just in this example on the aircraft. And the first thing to mention is that the deployment of sulfur aerosols should be at about 25 kilometers. We have no aircraft that can fly so high. Even the spy aircraft like Dragon Lady couldn't reach those altitudes. And deployment would require somewhere between 5 and 10 million tons per year continuously. If you stop, and that was mentioned before too, you have a big risk of a termination shock. Now, how would one do that? Well, there are proposals of what kind of aircraft could be developed for that. One example are the sail aircraft that could deliver about 25 tons to 25 kilometers height. But that would require some 4,000 flights per year if you have 100 such aircraft, more than 10 per day. I personally think this is unrealistic. So either the aircraft have to have a higher capacity or you need a couple of hundred aircraft. And below are examples I took from the literature. What did it cost to develop 747 and A300 aircraft? And you can see there in the red about 20 billion to produce about 100 aircraft per decade or more. So the cost would be significant even before we start producing the aircraft. So this is an example how big the challenge would be of deploying this kind of technologies and what the risks are. Next slide, please. Our fourth recommendation is that research on SRM conducted, but with the highest level of scientific rigor, responsibility, and in accordance with the European EU ethical principles. I think this is really important. So we need to create clear requirements, ethical requirements for the SRM research. There should be strict guidelines for the outdoor research, and it should be limited, as I mentioned before, because that itself can pose certain risks. And public, we recommend also that the public funding and the private funding for the private funding for the SRM should be additional to mitigation and adaptation. That there should be no trade-offs here. And we propose a moratorium on large-scale outdoor SRM experiments. It's to be determined exactly what large-scale is, but outdoor experiments pose certain risks themselves. Next one, please. Next slide. Yeah. Thank you. So our last one is that because of high risks, that there should be a strong participation of the scientific community in international assessments, international studies. We are proposing creation of citizen assemblies and other forms of initiating and supporting the debate, public debate on SRM in order to promote transparency. And last but not least, detection attribution modeling and methods would be required over a range of time horizons, including a range of deployment scenarios in order to understand better what the risks and opportunities might be. So that concludes the summary of the five recommendations. Thank you very much.
Thank you very much, Naki. And now we'll move to Dusan Hrenek from the Commission. Welcome. And you're going to make some comments.
Hello, good afternoon. Thanks for the invitation. And also thanks for very insightful presentations. And these presentations again confirm that solar radiation modification is highly complex issue, very controversial, also difficult to communicate, politically could be explosive, but scientifically exciting. And we are glad for the work of both groups and SAPEA. And again, scientific recommendations point out that we need a cautious approach. solar radiation modification is not a solution to climate change. Also, it's not substitute for climate change mitigation and adaptation. Only massive climate change mitigation and adaptation will lead to the fulfillment of Paris Agreement objectives. So we need to be very cautious to do our work in line with precautionary principle and address risk. So recommendations of group of chief scientific advisors and also European group on ethics are helping us for our policy discussions, so providing really helpful insights, and we value dedicated and thorough work that you did on this issue. So we have to work on governance of science and also potential deployment. We need to fill the knowledge gap, so it's necessary to study it more, and also address risk. So on this, we are thinking about detection capacity. So assessing if we could do something more on detection capacity. In the past webinars, but also today, we heard about importance of detection capacity. So it's something that we need to address. And as it is the final webinar, I would like to use this opportunity and once again express our gratitude to the group of chief scientific advisors, the European Group on Ethics, and SAPEA Consortium for excellent work, for peer review of all existing information, and for very insightful recommendations. So we are looking forward to work on this issue further, because this is not going to go away. It will stay. The work should continue, and we are counting on your assistance. Thanks a lot.
Thank you, Dusan. And please start putting your questions in the Q&A. I can see that we've got two. But over to Johannes, who's going to moderate the Q&A. Johannes.
Yes, thank you very much, everybody, for having a lively and intense discussion. We have 13 minutes, I guess, or how much do we have? Maybe a little less even for the discussion. So just let me maybe, I mean, some of the things we already reacted to in the chat, and of course there are many eminent experts also among in the audience. So thank you everybody for the insights and great discussion already going on in the chat. Let me still maybe comment on a few things, and then I identified so far three. I mean, more in-depth questions, which I would then ask Simona and Gabriel to answer. But just a few things. I mean, number one, there was a debate that there needs to be a focus on the CO2 emissions. And I saw a couple of you applauding Naki and the group of chief scientific advisors for their really very good recommendation. And I guess it's clear, and you'll also see it in the evidence review report. Number one is, of course, net zero carbon emissions, because unless that is reached, there is no solution to climate change. And you saw what Simone early on showed. SRM cannot work. I mean, in principle, maybe yes, but at large detriment only. So that focus is evident, and I think probably most everybody in the room agrees. There was a comment that research only based on models, and implementation remains a risk. And as Naki said, and Dusan as well, I mean, there's the do no harm principle, the precautionary principle. And I think, particularly when it comes to Europe, of course, we are confident that this remains the major driving force behind any decisions. Somebody was talking about the past emissions of aerosols by ships and volcanics as observational evidence. Of course, we evaluate this in our report, and it's also very much studied in the literature. But I think we should all agree that this is not a perfect analog. There are caveats. So I think it is important to note, yes, we learn from this, but it's not perfect. There was the question about research field experiments, etc. Yeah, sometimes called the moral hazard argument. The more we think about it, the more maybe people, voters will think it's a solution. But I refer to the past webinar on this because it's more in the social sciences humanity realm. The people sitting here, at least Simone, Gabriel, and I, we are not the experts on this topic. But of course, it's acknowledged and it's a large topic in the evidence review report. People were thinking a moratorium in place, and I can only reiterate right now, given the international agreements, which there can't be done, SRM cannot be done, at least by the parties to the Convention of Biological Diversity. We should be limiting further selling such risky projects. Sorry, that's a repetition of this moral hazard argument I already answered. Maybe Simone, there was this question early on. I think Gabriel already had a response in the chat, but maybe you can still comment on the complexity of models. Do they include biogeochemistry? Do they include ecosystem? What's the inertia of the oceans? And how do we validate models? Sorry, I spoke a lot, and you have maybe only a few minutes.
I can start quickly and then give it to Danielle. One thing is that the models, the Earth system models, include interactions with the whole climate system, the oceans, the atmosphere, the stratosphere, cryosphere. Ecosystem responses are not simulated necessarily quite well. We do have the land that can be quite complex. The models show various things from changing of trees, from, even reacting with chemistry and aerosols and other things. But certainly this is not perfect. More work needs to be done. And one thing I want to point out that putting understanding SRM and doing research into this topic really also is a win-win for model development in both ways, in understanding the effects not only of this, but also of climate change, because these interactions with ecosystem also matter, of course, when we study the effects of climate change themselves. So the research also in recent years has really improved climate models. I would say there's a lot of progress already been done in coordinating model experiments, bringing experts in that actually understand impacts like ecosystems, like people from underdeveloped countries to look at the things and the impacts. And that really brings new focus also into the question of climate modeling. And maybe one last thing quickly, evaluation is something very important we need to do. We do a lot. And one thing with these methods is looking at, for example, volcanic eruptions like the recent Hunga Tonga. There's a large assessment where people compare their model and model results. We do see how the models perform, and they do agree quite well with observations. But what we really need is be ready for the future volcanic eruption, be ready for observing changes in the climate system, especially when we reduce anthropogenic emissions of sulfur, which also trigger more warming, and as has been discussed, for example, in the chat. We need those observations to improve our models. Yeah, so that's all I wanted to say. Thank you.
Thank you. And then there was the question how to model the injection sites, the materials and timing, maximization of the effect and minimization of the side effects. Gabriel, maybe you want to address this topic.
Yeah, so admittedly, when it comes to the details of how the injections are modeled, of course, we have limitations in models. We don't fully resolve plume scale processes and really like the we really need high resolution models to actually properly simulate the evolution of the injections. But we can still learn a lot from the existing models. As Simone said, they're becoming better and better. Nowadays, we can already do simulations with 0.5 degree resolution. Models are increasingly complex. They now take into account the microphysical interactions, the coagulation, growth of the aerosols. So all that is taken into account. But of course, there are still large uncertainties, especially when it comes to alternative materials, for instance. That's a point that Simone also mentioned in her talk. One thing is the sulfur-based SAI, which is what has been mostly studied, but now there is increasing evidence that perhaps alternative materials may actually reduce some of the side effects from sulfur-based SAI. But these alternative materials, for them, we really need a lot more laboratory data, especially. And that without that, we cannot really improve the models much more.
Thank you. And then there was some debate around the termination effect. Simone, you quickly addressed this, but I think people are really interested in hearing more about this.
Yeah, the idea is really, should I take it? Yeah, I mean, the idea is really that if we are cooling the planet a certain way, the warming is still basically just backed through the reflection of the dimming, basically. And so if we would stop any of this intervention, right? We will go back to the temperatures that would be there without those interventions. And the discussion in the literature has been that the further we are away from the actual temperature, so the more we cool, the more devastating it could be to go back. When we stop the intervention, we would go back to the original temperatures. However, there's already a lot of discussion also that, first of all, we only want limited intervention to prevent that risk, as you already said. Secondly, it is quite unlikely that if an intervention would have started, that people would actually stop this completely. Even a stop of 1 or 2 years would actually not do much harm, because there's this inertia in the ocean to actually go back to those original temperatures. Only if we would not be able to recover such an intervention, we could see those effects. Does that help a little bit?
Yeah, I think so. And I think it is also, I wanted to just briefly add, if you go to Paul Crutzen, the chemistry Nobel laureate who put this up paper in 2006, one of his arguments discussing SRM was the termination effect of the pollution, I mean, the inadvertent aerosol pollution, just as a side note. Naki, there was the question whether your board recommended yes or no small-scale field experiments, or was in favor of yes or no small-scale field experiments, and maybe you can clarify this.
Yeah. Thank you, Johannes. Yeah, in principle, our view was based on the literature and the evidence review report that you just heard, that the outside of lab experiments should be limited. There might be some warranted cases to conduct that, but they should be conducted under very strict rules that would be developed, governance rules, ethical, social, and others. So we were very skeptical about large-scale experiments and do not recommend that those be conducted. Of course, the devil is in the detail. What is the difference between small scale and large scale also needs to be defined. But may I just take 30 seconds to make another comment that's related to that? Given the large uncertainties about SRM, we know with high certainty that limiting emissions to net zero will stabilize climate. I mean, this is a big contrast. That strategy will definitely work, and I think everybody agrees on that. How do we go down is an interesting issue. But we, in the last century, decades ago, when we started modeling from the mitigation point of view and adaptation, climate change, colleagues introduced what we call backstop technology. Technology that doesn't exist, might have very high costs, but could potentially solve the problem. So to be honest, I see this little bit like a backstop technology. That's why it's good to do research on it. Who knows whether we might need it or not. Research is also good to have expertise in Europe about the SRM should somebody else deploy it. So I will stop here, Johannes. Thank you.
Thank you. And maybe one last, before the conclusion, one last question was, somebody asked, the earlier SRM might start, the slower the scale-up might be. And maybe, Gabriel, you can comment on this.
Yeah. So if I understand the question correctly, so they're asking whether, starting earlier would actually make necessary to do less SAI or SRM in general? And the answer is it depends. It depends on our on the evolution of greenhouse gas emissions and whether we already are overshooting, and it also depends on the target climate, right? So we want to do we want to stay below 1.5 degrees Kelvin? If you're way above that already, by say 2050, then yes, we do have to do a lot more SAI than, for instance, if we had started in a decade from now. But again, it really depends on what we do with greenhouse emissions. Again, also the side effects, as I showed in my talk, they also depend critically on how much warming we want to offset, and therefore how much SAI we would do, or SRM in general.
And then, again, a couple of very interesting questions on governance, but again, refer back to the previous webinar where the experts were contributing. I think it's really interesting, and also the evidence review report, if you like. There's a lot on the governance issues, and those of you who commented are completely right. It's a very, very challenging problem, governance. Louisa, am I concluding? Are you?
I'll conclude. Thank you so much. Thank you to today's speakers. Thank you to the speakers from the previous webinars. That wraps up the webinar series. Hope you've enjoyed it. Thank you to the advisors. Particular thanks to Dusan Hrenek, who's spoken at every single one of our webinars. Thank you so much. And thank you to you, the audience, for such a lively debate through the chat. Absolutely amazing. Thank you so much, and goodbye. All the best.
Thanks a lot.